The Optica Online Industry Meeting on OLEDs and micro-LEDs will take place on Tuesday, March 4, 2025, starting at 10 a.m. Eastern, 4 p.m. in Europe, and 3 p.m. here in the UK. Our online discussion will focus on the latest developments in OLED and micro-LED technologies to cutting-edge displays, technology shaping the future of visual experiences. OLEDs have established themselves as the standard for high contrast, flexible displays in smartphones, TVs, and wearables. Yet, challenges remain, particularly in the development of blue emitters, which
I'm afraid we have lost Jose.
Yeah, I can't hear him either.
Oh, well. Well, then, anyways. Well, unfortunately, technical glitches happened. I believe that Jose will be shortly with us. Nevertheless, I am very happy to see so many familiar faces and this meeting. First of all, of course, of all of our speakers. I also see Reinhard Volkel from the focus light. Reinhard, don't disappear. And many of the very, very familiar faces from across the industry. It's a pleasure to have you here. We're about to start a very exciting 90 minutes discussion, live discussion, on the recent progress and advances on the micro LED and OLEDs technologies. So many of you know these are the technologies that are aimed to power the next generation visual experiences, starting from, of course, VR and, of course, AR and everything in around. Jose is coming back to us.
Thank you very much. Thank you so much for being always prepared to jump in when the IT issues are not with us. Mobile Congress is happening. Things are extremely viral right now. Everything is going on the manufacturing of next generation portable mobile phones. And we want you to take a break for the Mobile Congress, for those of you who are with me here in Barcelona, to connect and to talk about the challenging parts in the manufacturing of next generation OLEDs and micro LEDs. So for the next 90 minutes, these are the rules of the game. We are going to analyze two use cases in the field of displays, one coming from Expanseo and the other one coming from ELAX displays. We want to understand what they need from the industry, and we're going to match those with the technology of all of you in the room. We have about 250 people registered for this meeting. In particular, we have selected a few of our corporate members, but everyone in the room has a right to play here. We want to understand your answer to the Optica question. What can you do for the others, and what can the others do for you? It is quite an exciting roadmap to organize these online industry meetings. We are getting hundreds of registrations for each one of our events. In a couple of weeks, we have our event on fiber sensing. We had the food event on the 15th of April. Write your calendar for that one. And all the other topics are already selected from now until the 10th of February. If you want to participate or speak at any of the upcoming online industry meetings, all you have to do is to tell us what you want to say. And of course, if you are a photonics company, join Optica, optica.org/join corporate. We need you to support us. If you want us to continue doing our job, you need to become a corporate member. That is the only thing we ask you. This is the result of hard work by a great corporate team where we provide this access to our network, market reports, fantastic, I would say the best events in the world, discount to exhibit and to attend, promotion of your technology, and lots of engagement opportunities with the rest of our companies. Remember, what can you do for the others? What are the others going to do for you? We had the largest industry library in any of the other industry associations. All the content here is fully available for corporate members, market reports from leading market analysts, all the presentations ever given at an industry event, different tutorials, all the different presentations that we have been seeing in the online meetings. Everything is there for you. Everything is fully accessible for you. This meeting It's also going to be live streaming YouTube at the same time as we are here in the Zoom room. So allow me to say hello to the YouTubers of the world. Hello, YouTubers of the world. If you have any question during the next 90 minutes, write so in the chat and I will, of course, read it in the room. And this is, of course, also valid for the people here with me in the Zoom room. During this meeting, we're going to have 90 minutes for you to interact with each other. Use the chat to talk to each other. If you have something to say so in the chat or in the Q&A button, and we will make sure that you voice your question yourself, because ultimately, this is not a webinar. This is an online discussion between all of you, and we want to make sure that during the next 90 minutes, you find potential partners, suppliers, customers, investors, and perhaps some talent. Let's start. And I would like to start by welcoming the person who made this meeting possible. She is our Director of Optics and Optical Systems at Optica, Dr. Olga Ras. Congratulations on putting together a fantastic event. What's going to happen over the next 90 minutes? And you have some big celebrity to announce.
I have indeed. Thank you, Jose. I have a very big celebrity to announce, and I'm really proud of it because, unlike in many other meetings, actually for this meeting, we decided to, and I was lucky to get one of the tech experts to really look not only at the technologies and the detail, but also to be able to zoom out and tell us a little bit more about what's generally going on in the field of the micro LEDs and OLEDs. And I believe everyone who is in the room already knows who I'm talking about because I'm talking about Ron Mertens from Micro LED Association. Ron, welcome to the group. Welcome to the meeting. It's the first time that we have you around, and to be honest, I'm really nervous and very proud. And I'm really looking forward because you as the tech person, as the general director of the Micro LED Association, and also as the provider of the consultancy services for OLEDs and perovskite, I think you're really a true person that knows what's going on in the field. And I believe many people in the room would be very interested to know what you know. So please, the attention of everyone is yours, and we're really much looking forward to the recent updates and news in the exciting world of the micro LEDs and OLEDs.
Thank you, Olga. Now I don't need to introduce myself. I understand. You've done a good job. I will share my screen now. And I know Olga only gave me 5 minutes or so to
Don't
do
worry,
this.
no pressure.
No pressure, but I will try to be quick and to the point. So let's begin. So first of all, we'll begin with OLEDs. And I've been asked to show some of the recent trends or what's going on in the OLED industry. So as you all probably are aware, OLEDs are doing good. I mean, the display industry has been adopting OLEDs very nicely in the last few years, maybe 10 years or so, to the point where over 50% of smartphones are now using OLEDs. We see great inroads into wearables and tablets, TVs, and monitors. There's a lot of room for growth, but OLEDs are doing very well. And in the last few years, we have seen three main drivers for the OLED industry. First is device efficiency. So we talk about power consumption, reducing the power consumption of OLEDs, and to lower the production cost. That's always a driver in the display industry, which is mostly a commodity industry at the end of the day. And the drive into new adoption into IT displays, into laptops, monitors, and tablets. This is rather new for OLEDs, and this is something we're going to see in the next few years, and we're going to go more deeply into that. I also added a little bit about new flexible form factors. So we've all seen these foldable smartphones in the last few years that has been received rather well in the industry. And now we're starting to see new form factors like rollable OLEDs and maybe novel kind of foldability and flexibility, which is not something that we actually see as a main kind of driver for the industry, but this may surprise us because foldable OLEDs have been very nicely introduced. So this is something to consider. So let's talk about device efficiency. So really in the last 5 years, I think that the display quality of OLEDs has been excellent and pretty much compared to a perfect display in most environments. Also, we see these displays as being very light and thin and flexible. So the focus of the industry has mostly been around efficiency. We are seeing a lot of new technologies that are being developed and introduced now to reduce the power consumption of the OLEDs. So we're talking about things like tandem architecture, where you use 2 stacks or even more stacks of OLED emitters, one on top of the other, to increase the brightness and, more importantly, to reduce the power consumption. We see the introduction of new emitters and the development of new next generation emitters, mostly centered around blue emitters. So these are expected to be here by the end of this year commercially, which will reduce the power consumption by around a quarter. So it's quite efficient and important. We see the adoption of micro lens arrays, which are these very small lens that you put in front of every subpixel in your display. Again, the main target is to increase the light output out of the display, again, to increase the power efficiency. We see the adoption of deuterated OLED compounds, of new production processes that do not use masks. And the list goes on, and the main point is that OLEDs are efficient, but they will get much more efficient in the next few years. So especially, this is aimed for developers of next generation display technologies like micro LEDs. OLED is a moving target, and the efficiency is getting better and the brightness is getting better. And we'll talk about that in a minute. The next main driver for OLEDs is IT displays. And so we talked about it, how OLEDs are already here for smartphones and wearables, and the next battleground is IT displays. So Apple already started adopting OLEDs in the iPad Pro last year, and they have a roadmap to fully adopt OLEDs in all of their IT devices. It will take years, but we certainly see an increase in adoption in all major brands. And we see the industry moving towards larger scale production, which will enable lower cost production and then more adoption. And this is certainly a big topic in the OLED industry in the years to come, IT displays. Yeah, and that's what I wanted to talk about with OLEDs. For more information, you can take a look at OLED Info, our publication, and specifically the OLED Toolbox, which is a compilation of information we cover for the OLED industry. This could be a good resource. I'm sorry that I'm running so fast, but it's a lot of things to discuss. Now, as we turn to micro LED, so this is the main topic of today. Micro LEDs are still at a very early stage. In most points, at most cases, it's not really being commercialized yet. But we do see the industry focusing on 3 application areas, which are AR, automotive, and large area TVs. I think that one of the main points to understand about the micro LED industry is that at this stage where the costs are very high and there's still a lot of challenges in production, what we feel is that the areas that will be able to actually adopt micro LEDs is the areas that there's a real need for the micro LED performance increase. So if you talk about micro LEDs, the main ports are increased efficiency and brightness, increased lifetime. And these are the areas, in normal areas like smartphones and TVs, there's not a clear need for this kind of performance. So it will be hard to actually move the industry to adopt a very high cost display technology. This is different in AR again. The main point to understand about AR is that there's no market yet. So it's kind of, pulling from both ends, and we'll see where this takes us. And the automotive industry is highly interested in micro LED because of the long lifetime, the stability, and also the high brightness. And in large area TVs, we take advantage of a different, kind of property that micro LEDs bring, in that they can enable seamless production. So you can tile small displays and make a very large display. And this is starting to get interesting in the industry. So it's important to understand that there are still technical challenges that need to be solved with micro LEDs, especially around several kind of platform decisions and architecture decisions, such as how to achieve full color, how we're using native red emitters, are we doing color conversion, maybe look at next generation color tunable LEDs. These are still open questions. How do we get the production costs down and meaningfully down from what we have today? And how to keep the efficiency up even as we go to very small sizes below 5 micron, which is needed especially to reduce the production cost. So we still have these open questions, and the micro LED industry, it's at this great stage where we have this, flux of technologies and a lot of different innovation solutions for a lot of problems. And it's great to see the advances that we see in the last few years, but we still have some road to make. And I wanted to wrap this up and say that the main challenge for micro LEDs as we see it is the competition with OLEDs. So for most display applications, OLED give us great performance, actually kind of perfect display quality. They're very low cost in production and also the cost of adoption for OLEDs. And they're actually good enough for almost all the applications. In addition, OLEDs are moving fast. We talked about increased efficiency. We have several generations of new technologies coming up that will dramatically increase the brightness and efficiency of OLEDs. And this is a concern for micro LED developers. And what we can suggest for micro LED developers is to have a strategy where you have to focus on areas where OLEDs do not provide the good enough solutions. And we talked about this, like AR, certainly, automotive, maybe very large area TVs. Another strategy could be to focus on very premium segments, such as luxury smartwatches or ultra-large TVs, again, as an example. And finally, and not least, is to leverage the unique production processes and the customization options that microLEDs provide. And this could be the key topic for many microLED developers, and how to actually take advantage of the different processes and the decoupling of the different processes used in microLED to enable different kind of production environments. And that concludes my talk. Now, Olga already invited you all. Yeah, we are having the second microLED Connect event in September in Eindhoven. And this year, we're going to co-locate it with an AR and VR focused event as well. Our event brings 2 days of a conference and exhibition and another day of tools and master classes. But most importantly, and that's why we call this microLED Connect, we want to really connect the industry together. In Eindhoven, we have this great venue and a great atmosphere to really talk about microLED innovations and also meet the entire industry and all the next generation technologies that being around. The first year event was quite good. I think it was excellent, but I cannot say so myself. And we'll welcome you all to join us in September in Eindhoven. And that concludes my talk. Thank you.
Thank you so much, Ron. Yeah, and we're also a proud supporter of the event, and I also hope to be there. You've mentioned that with the OLEDs, the main so one of the directions of the development are actually new materials. So would you say it's the main interest or the main direction for developing OLEDs further is really chemistry?
So chemistry is definitely one part of it. It's a very challenging kind of process. So companies have been developing a more efficient blue OLED for the last 20 years and haven't been successful in actually doing so. So it's a huge challenge. We currently are quite optimistic about next year, but the number of players that actually attempt to develop next generation materials is very small. And there's some challenging IP environments in the OLED industry in this topic specifically. So while we see 2 or 3 companies that have a very good chance of succeeding in introducing these new materials, it's not a wide kind of process across the industry. Unlike other areas such as new architectures for maybe maskless production or polarizer-free OLEDs, which we see more companies trying to develop and adopt.
If you look, it's a little bit, let's say, off the charts, so maybe you don't want to answer the question, but if you will think maybe of 2, 3 really display developers or novel tech, whom would you call as the companies to watch? For OLEDs and micro LEDs, you may also just smile and say, that's okay.
But for micro LEDs, I have a lot of friends here in this room that I cannot say, this company or the second. For OLEDs, basically the display industry, the OLED industry is very small. I mean, the total number of players, you can count them on a single hand or maybe a single hand and another finger. And all of them are making very good progress in all the areas we covered. And it's very interesting to see that all the OLED makers, if you look at Samsung, LG in Korea, and the companies in China, in BOE, Tianma, and Visionox, and CSOT, Ever Display, most of these companies are using the same process and are progressing on the same route forward and are all adopting all the next generation technologies. It's a very cutthroat business. In micro LEDs, it's a lot more interesting because we see a lot of architectures and platforms and different kind of processes, and it's going to get much more interesting, I think, in the next 3 years.
Okay, because as you mentioned, there are a couple of the players that are doing the OLED chemistry. I would actually like to bring to the floor and to invite the Noctiluca to join the discussion, who is one of the players that is developing chemistry for OLEDs specifically. And I also know that you have quite some progress on blue OLEDs that Ron mentioned. So Alicia Zelinska, welcome from the Noctiluca SA from Poland. Tell us a little bit more about the Noctiluca, and of course, what are your solutions for the OLEDs world?
Good afternoon, everyone. Thank you very much for the invitation. It is a true honor to be here today, and I will share my screen with you. Just a second.
Ron, prepare your questions.
Okay, great. I would like to take this opportunity to introduce our newest product, NCIL4. However, beforehand, I would like to introduce Noctiluca. Noctiluca is a Polish deep tech company focusing on designing and producing materials for the products of the future. We are a traded company since 2022, and at the end of last year, we moved to the main board of Warsaw Stock Exchange. Currently, we are operating in main 3 areas. First pillar is our own research and development focus on new TADF emitters for OLED applications. Second is CCRO services, providing solution in other fields than TADF emitters. Finally, we have launched custom synthesis supported by sublimation services. This enables us to synthesize any IP-free organic material in the field of optoelectronics. One of the hottest topics in OLED world is a new blue TADF material, which is expected to improve device performance and extend the lifetime. Noctiluca, through its own in-house research, is strongly focused on this subject. However, within the time, our approach to the race for blue has also evolved. Emitters are one of many layers of OLED stack. Layers responsible for injection of electrons and hole and their transportation through the entire device also require high quality materials, and they have a great importance for overall performance of the device. This is why Noctiluca is aiming to be a designer and producer, not only for emitters, but also for materials for the products of the future. NCIL4 is our proprietary and patent-pending material that has been developed as a solution for a real industrial need, and it is our proposal for electron injection material. It is already being used as an alternative to the well-known LIQ in monochromatic blue lightning application by one of our industrial partners in Europe. The material is also in testing phase with other partners from China and Taiwan. Also, its performance was proved by 2 independent research teams in Korea. Based on that, we strongly believe that NCIL4 might be a solution for lifetime problems in blue OLED devices. After many internal tests, we found benefits of NCIL4 in both the performance and in the device and as a material alone. On the material level, NCIL4 shows very similar HOMO-LUMO energy levels to LIQ. This allows direct exchange without the necessity of changing the stack architecture. The material can be delivered as high purity sublime grade. On top of that, NCIL4 dissolves in polar solvent, what might be an interesting feature for printing application. Devices based on our solution have significantly longer lifetime in comparison to LIQ-based references. We have also observed beneficial reduction of working voltage and therefore lower power consumption in the devices. This was achieved without compromising other parameters and without any influence on EL spectrum. We've tested NCIL4 in 2 ways. First, as a direct exchange with LIQ on the EIL level, and second as doping to ETL. The simple exchange with LIQ on EIL level, shown in the graph as devices 1 and 2, results not in several or dozen percentage improvement, but in 5-fold lifetime increase. Second set of experiments, devices 3 and 4, led us for even further lifetime improvement. We've reached, in comparison to LIQ-based devices, improvement in lifetime by 15 times. These both sets of experiments proved that NC-EIL4 can be used either as EIL material alone or as a combination of EIL and doped to ETL. This is our proposal and contribution for the race for blue from the perspective other than emitters, of course, on which further research at Noctiluca is ongoing. We strongly believe that this will lead us to increase numbers of EIL materials in our portfolio. Thank you.
Thank you very much for being here with us. Noctiluca has been engaged with us for many years. Stay with us today because we have many partners that are going to come on the room for you. You're going to see people who are doing printing of materials with new printing heads like Expanseo. You're going to find, like Scrona, you're going to find great partners today. But before that, this is, of course, a meeting driving by the market needs. And the market needs today are shown by two companies that are giving us goosebumps. I want to introduce the first integrator in the room today. Looking for partners in the field of smart contact lenses. I'm talking about a company that everywhere they go, everybody is quiet because they really want to listen and find out what their secret is. They're not going to tell us their secret, but they're going to tell us how we can make them be even greater than they already are. I'm talking, of course, about the company Expanseo. Valentin Volkov, tell us about the way that you want to do the next generation of computing using super smart contact lenses. The floor and the attention of everyone, Valentin. We are global today. We have people in Australia, in New Zealand. We have people in the US, in Europe. This is your audience. Enjoy.
Thank you very much. Now I really feel myself under the pressure. And the responsibility is huge, of course. Thank you very much for this great opportunity to present our company. Let me share my screen. Yeah, can you see it?
Crystal clear.
Yeah. My name Valentin, and I'm one of two co-founders of the company. We are Dubai-based deep tech company called Expanseo. This strange thing which you see on the screen, it's not extraterrestrial flying object. That's actually our smart contact lens, which we are developing within the company. And I don't know, maybe someone is these days actually at Mobile World Congress, because we have actually our booth and almost all our prototypes are there. And actually, as I know, today we were officially announced the best MVC project by, I think, Technoradar and Slash Gears. So, I mean, those who are in Barcelona now, they have a real chance to go to our booth. It's number 6116. And you can actually try the lens. Today, I will talk mainly, of course, about challenges which we face once we actually trying to integrate a micro display inside the lens. It sounds almost like something very much undoable and crazy. I will try to convince you today that actually it's possible, even though still many things can be improved, of course. But of course, our lens, they are a bit wider than just a ER/VR device. They're also like different other functionality, like it's a very private biolab integrated inside the lens. There are some optoelectronic components, antennas, mirror interfaces integrated in many other things. So, but let's talk a bit about micro displays. Yeah, somehow I'm trying to. Okay, yeah. Sorry, let's try one time. So, why actually LEDs? And because we believe that the next computer will be AR gadget. And we actually think that it should not be necessary VR glasses or helmets. Actually, we believe in something which will be seamlessly integrated and will give you kind of very private and very unique experience. So here we are talking about smart contact lens. And we believe that this innovative approach be able or is able to solve main issues with augmented reality industry issues. It's like brightness outdoors. Well, everyone knows that once you are wearing smart glasses, and if the sun is up, then of course it will this shining will significantly deteriorate a contrast of the image. So once the sun is up or outside illumination is goes directly to your eye, then of course you need to increase the brightness of your display. Otherwise, you will lose the contrast. And of course, this will directly kind of bring the next problem. I mean, once you are increasing the brightness, you are running out of the batteries, you produce some overheating and so on. And we actually believe that once the display became directly integrated or placed on your eye, then the coupling efficiency from the display to eye will increase significantly, almost order of magnitude, which of course will allow you to suppress the power consumption and actually solve all those traditional problems with the deterioration of the contrast, overheating, battery running away issue. And plus to this, of course, it's eyeball situation. Of course, once you are dealing with traditional displays, screens integrated at the surface of glasses, there is always a certain distance between the eye, of course, and the display itself. And the angle, the distance and the angle will determine the eyeballs. And basically so obviously, of course, once we put the display directly on the eye, then this distance goes almost to zero, which in principle makes your eyeballs infinitely big. Well, they're of course not infinitely big, but as big as possible in principle. And then, of course, another situation. Imagine that you have glasses and those display just in front of you. So once you're watching looking on a display and looking through the display, you kind of either in focus or out of focus, basically. So once you put a display on an eye, you actually, according to the traditional, of course, optical laws, you will not be able to see something. I mean, unless you will integrate this display with some smart collimating system. And then, of course, all the image, all the rays, you can say, from the display will be parallel. They will go through the eye lens, and they will create an image on the retina directly, which means that it doesn't matter where you're looking, close to you or far away, the image created on the retina will be always in focus. How does it work in principle? As I mentioned, evolutionarily, we are very good at looking objects which are kind of far away from us. And once you start to approach it closer to eye, so first of all, of course, you will start to adopt your vision. But at a certain moment, once it's really close, you will not be able to see it, which means that once you put your display directly on a contact lens or within the contact lens, basically in direct contact with your eye, so there is no chance you will be able to produce any image under the usual conditions. So you need to somehow collimate the radiation which goes from the display. And of course, it can be done with some diffractive elements, for example, grating, collimator, maybe holographic element. And at Expansive, we actually simultaneously developed several approaches, but one way or another, it's some smart meta surface, which actually collimate the radiation from the micro display. makes all the rays as parallel as possible. But there were some limitations in this way. And then the important requirement that it should be relatively thin. I mean, the display should be relatively thin, and the micro collimator system should be relatively thin. Altogether, they'd be thinner than 1 millimeter, because in the end, you have to somehow to pack all those components within a very compact form factor, contact lens, which is not thinner than 1 millimeter at the very thickest place at the very center. So let's show that how actually it works. That's the concept, basically. Of course, we would need some micro display integrated inside the lens. And then this micro display should be integrated together with collimating system. At this particular concept, you see that our display is actually smaller than the collimator itself, but in reality, at least right now, it's not the case. I would say it's exactly the opposite, because we are trying to work now with the commercially available micro displays. And then if you manage somehow make it small enough and integrate inside the lens, then what you will see here, that's actually some kind of image, which if you will take a closer look, looks like some letters. That's actually image produced by the micro display system integrated inside the contact lens. And just to show that actually, that's let me first go to this one. I will show you some, just to prove that I'm actually not that I'm not talking about science fiction. So it's not science fiction, it's more like a rapidly developing reality right now. So that's our lens, one of the prototypes of our lens. It's actually a GBD-based micro projector integrated inside the contact lens. Of course, let me show. We kind of now approaching it. I mean, there should be a very special camera. We have it called like artificial human eye, because if you use just a camera from your smartphone, it will not really give you a real experience. But so that's, as you can see, it actually works. We can do some different things. It could be some text, could be some casual gaming. We can actually display some useful information. I mean, as you can see, the resolution is not as good, and I will just a bit later I will explain why. So you can play Tetris, for example. That's the most important, of course, achievement, which we demonstrate usually on different events. It's okay, so it's some social case. It's almost done. Yeah, let me now jump back to my previous slide. I mentioned just to introduce the difference between smart glasses and smart lens in terms of image formation. Of course, smart glasses, they are far-field device, which means that again that the display is far away from the eye, let's say. So usually you have some in-coupling area of the smart glass, out-coupling area. Then, of course, at each of those areas, you will have significant losses. So the total coupling efficiency, which actually the amount of information which actually delivered to your eye in the end is somewhere around 10-15% of the initial signal which comes from the display. That's actually exactly what makes it very beneficial in terms of influence of the outside illumination. And as a consequence, of course, it will have all those problems with energy consumption, bulky batteries, and so on and so on. So in case of smart contact lens, the situation is opposite, I would say. So you have a display integrated, of course, with the collimator, which is placed directly on the eye, which means that the coupling efficiency from display to eye is like around 75%. which means that you don't really need high brightness of the display. Whatever comes from there will be efficiently delivered to your retina, which means that actually you can put down brightness, and it will be significantly less deteriorated by the outside illumination, like sun, some artificial illumination sources. Here, let me go to the excellent. Yes. So what technical specifications? As I said, I mean, the smart lens with the display, which I showed just previously on the video, it's based on this GBD micro LED micro display with a pixel pitch 4 microns, and the size of the display is pretty big. And actually, that's currently the smallest display available on the market, which we managed to grab and bring to our lab. It's like 4 by 4.5 millimeters in size, lateral dimensions. So, and our collimator is actually significantly smaller than that. The diameter of our collimating system is 250 microns. So, which actually, that would make this problem. So actually, collimator is significantly smaller than the display area itself. So, which makes our screen area being just only 40 or 34 pixels in diameter. So it's what, or 72 pixels in here when it's viewed when it's viewed viewed. So which means that actually field of view is not that impressive, but still it's like more than 24 degrees or more, a bit more than 50 degrees when you are looking around. So the resolution is not that good, 1.4 ppd. So, and the concept which we are developing right now, it's more like we are not actually going to really integrate it into the final prototype, just to kind of to check the boundaries which we are working right now. So we are using another display. It has a better pixel pitch, 2.5 microns, and another collimator, which is actually has a huge diameter, it's 2 millimeters. It also has a significant length, but just to show that actually in this case we can significantly increase the screen area. So then we have actually like 800 pixels in diameter, and field of view in this case immediately became almost 70 degrees, and the resolution is 12 ppd. And then the target parameters, which we actually going to achieve somewhere closer to the end of the next year. So that's a micro display with a pixel pitch less than 1 microns. We will create a collimator with a diameter around 500 microns and length less than millimeter. And then it will give us a good screen area with around 250 pixels in diameter, with a field of view more than 90 degrees, and the resolution, which will be estimated around 1.5 ppd. And yeah, that's the requirements which we are, I mean, for the micro display which we are looking right now. So of course, it would be nice to have a full color display, but even a monochrome one is good. I mean, the green one is it's a cool color. Looks like a matrix, something inspired. Then the pixel size would be nice to have less than 2 microns, pixel pitch less than 3 microns, pixel matrix diameter is not more than 0.5 millimeter or 0.25 by 0.25 millimeters. And the device size would be nice to have less than 1 millimeter, and overall thickness also less than half of the millimeter. Then, of course, usually, of course, it comes with a protective glass, optional, but we are a bit limited in terms of thickness of that part. It would be nice to have either remove it or have it not more than 0.1 millimeter. And yeah, I'm thinking I'm running a bit out of my time, so
No worries, Valentin. No worries. It's always, I mean, it's always impressive to hear your futuristic presentation. But I have to say, for a futurist, you're already doing quite substantial progress. And we actually have
Thank
quite a
you.
few questions. And I'll start with the beginning, and it's Ron, who is very curious about your specific materials that you're using. Ron, please go ahead and ask your question.
Yeah, hello, Valentin. So I have two questions. First of all, we know that you've been developing a 2D material based system for the substrate. It's similar to graphene. I'll be happy to get an update on that and whether it has any effect on the optical path or the performance. And the second question is that in a final product, will you be able to actually use what I would call a normal micro LED display, like the JVD display you mentioned?
Yeah.
Or do you need to have something that is more suitable for, used in a contact lens on the body, things like that?
Yeah. May jump to the second question, and then I will talk a bit, elaborate on the first one, because first one it's more like more on fundamental side, and I can talk for a long time. I mean, regarding the display, indeed we need something which is relatively small, significantly smaller than those GBD displays that are available on the market. So actually now we are trying to launch a project together with Fraunhofer Institute and to develop our own micro display with the size like not more than 1 by 1 millimeter, let's say, in the lateral dimensions, and less than half of the millimeter in cross section, let's say. And it looks like it's doable. And the companies that already kind of were before us, like Motor Vision, maybe many of you heard about this, they kind of already succeeded in this. So it's doable, definitely. But now we just need to repeat this and get access to this small micro display. And regarding the low-dimensional materials, yeah, that's our specialization, I would say. So all those optoelectronic components that related to collimation and diffractive elements, we produce them in our state-of-the-art lab here in Dubai. And yes, they involve a high refractive index low-dimensional materials. Because that's the only way how we can in the end squeeze all the device within the dimensions. I mean, to make it less than 1 millimeter. Actually, we would like to have it less than half of the millimeter. It's even this one. It's actually it's a big one. So I think our best result now we make it as small as 200 microns. I mean, this collimating system, which actually that's a good size. And it's actually based on those advanced materials. It's not really graphene, graphene, it's like a semi-metal. So, but the Nobel Prize was obtained, like, I think 2010. And for the last 15 years, there was like at least 200 new low-dimensional materials. So it's nice. Now it's like a new table of chemical elements. And to say the truth, it's a challenge to go, because many of them actually they're not properly studied, and that's what we also do. We investigate the optoelectronic properties of those materials, then we combine those materials, we tweak them. We also have our own clean room facilities where we can do a nanostructurization of those components, and then we integrate them into the contact lens. And as a material for the contact lens itself, that's certified polymer materials that are commercially available.
That was also my question.
Yes,
because
it's very important to. Yeah,
it is because
it's very
like the molder.
important to use certified materials, because in the end, one should keep in mind that contact lens it's a medical device. You have to go through the medical certification and medical approval, and I would say that's the most challenging part of our project, because it's difficult but possible to create this next generation of electronic gadget, but to convince our medical colleagues that it's kind of not dangerous for people. That's the most difficult part.
Yeah, and especially in connection that most of the modern contact lenses, right? There's this polymer flexible lenses, and no one wants to go back to the rigid
Some of them
solutions.
they are soft, Others are rigid, but in both cases, of course, it's a polymer materials. They are highly breathable and let's say conductive for oxygen and yeah, for also for liquids. So there are some technical issues how to put the electronics encapsulated in a proper way and design them all together. I mean, because in the end, they should all operate together. I mean, and there are plenty of components starting from the antennas, batteries, solar cells, biosensors,
Yeah,
micro
it's a
display,
complicated
and now
system.
yeah, it's
Actually, since you've mentioned Mojo and their original project for the contact lens, we have a very interesting question from Zahir Alpaslan from Global Foundries. Zahir, would you like to unmute yourself and ask your question? It's a provocative one.
I was just wondering, there have been many companies that came before Expansio, and for example, most recent one was Mojo. What have you guys learned from them in terms of, technology difficulties and market difficulties that they faced?
yeah, Mojo, they are pioneers actually. And then, of course, before we jumped into this crazy business, we deeply studied all their. I mean, it's not that much actually available, but we tried to grab all the presentations available, all the patents, and studied everything. Of course, we also introduced. I mean, we personally know guys, and we also know their partners like Minicon, for example, some other companies that involved deeply into the project. So to some extent, of course, we also signed all possible NDAs and all other things. So we really respect what they did, and we use those achievements as a background to basically we are trying to involve our unique expertise in advanced materials and nanophotonics to move the idea a bit further. Yeah.
Thank you, Valentin. And we actually have further question. Zahir, was your question answered? Or do you have more comments?
I think it might be a better idea to catch up later.
We will catch up, I think, all of us in September again. Meanwhile, we have another question from Alexander from Alice IDEOS Semiconductor. Alexander, go ahead.
Yes, thank you. Real quick, I understand you're not intending to build the display yourself. Is that correct?
It's difficult and then very pricey, unfortunately.
Yes, and do you see anybody in the market being close to the pixel sizes you are looking for?
Could you please repeat?
Do you see any displays, any vendors developing displays which are coming close to pixel pitch and pixel size you're looking for?
Yeah, of course. First of all, it's a motivation itself because the company did a pivot and now they are developing those smallest micro displays. The only problem, because I think the Mojo now they are more oriented on a standard augmented reality devices, like first of all, of course, glasses. And for glasses, you don't need those teeny-weeny micro displays like 1 by 1 millimeter. And once we start I think they have a technology, but we are still kind of trying to convince them to launch the project, but not yet succeeded. But in principle, I mentioned the front offer institute. They actually, we are discussing with them the kind of proof of concept projects, and we actually even ready to involve some significant funding into this. And hopefully within some recent time, maybe something we will be able to have something which have much better form factor, compared to other micro displays available on the market.
And
Right,
speaking
thank you.
about solutions already that are on market, Alexander, how about your own solutions? Because you're also a speaker, and I know that you're also active in the field. So tell us more about what you do and what are your solutions for the micro LED world.
Shall I also bring up my slide?
Yes, please.
Yeah. All right. What Elos does is we develop epi wafers. So we start at the very beginning of the value chain. And that is important because if you don't get the quality right there, you are in trouble for everything else which is coming. I apologize because we tested it earlier and now the sharing is not showing the slide. Just give me 1 sec.
That's okay.
So yeah, like Olga asked, what are we doing? We are starting at the very beginning of the value chain with the base material for all the micro LEDs. So I hope everybody can see my screen.
Yes.
Okay, this makes explaining it a little bit easier. So basically, when you think about the value chain and the supply chain, and I do this very high level, right? So you start with a material, which is the epi wafer, and then that is today typically grown on sapphire substrates, rather small diameters when you compare this with conventional semiconductors. So we're looking at 100, 150 millimeter instead of the 200 and 300 you would have in typical semiconductors. And then you bring those into chip making. And one important thing to remember is whatever bad you have on the epi wafer, you cannot correct in any of the subsequent processing steps. Then you go into integrating that into a light or display engine, depending a little bit on the application for micro LEDs. And then it goes into all the fancy products we all carve for and we all want to sell in millions. Now, the roadblock today is really that because you have bad uniformity as a start, you don't have the best possible manufacturability excellence in the supply chain when it comes to manufacturing the actual micro LED chips. For example, what Valentin was talking about, these small pixel sizes, right? That is something which you can never accomplish in a normal LED facility. You need to go to semiconductor environments. And then whatever yield you have to start with, it only gets worse because at every process step you have a yield loss. Even if you are at 99.99, 59 or even 69, you always have a yield loss. And that accumulates to all of us having this pain in seeing products out in the market which work, reliable, that you don't have any dead pixels, and which comes at affordable cost. And what we focus on is basically getting this first thing right, the first building block. And that is what our customers work with. There's 200 and 300 millimeter gallium nitride on silicon epi wafers. They have the big disadvantage that it's more difficult to grow on silicon than on sapphire. But they have the big advantage, it allows you to bring these wafers into standard silicon lines. And that is simply the world's most efficient and high-yielding process environment you have. And that basically gives you the right foundation for every subsequent step in the supply chain to not have any unnecessary yield loss, which then enables you to actually make devices in volume with high yields and acceptable cost. And that is our one-pager pitch. We try to nail it down to what is the core of what we offer, and that is getting the industry the right starting point.
Thank you very much for being with us today. It is great to have you as a corporate member of Optica. What solutions are there today to understand, to qualify the yield of a gallium nitride or silicon wafer?
Well, the yield management starts basically during the growth of the epi wafer. So you have sensors which measure the growth, which is actually quite tricky. It's a very long process. We're talking about hours and hours. So not the typical semiconductor process, which is like basically minutes or even seconds. It's hours and hours. So you need to be very careful to get this process right. And then you do a lot of on-wafer measurements. So this is checking crystal quality. This is checking the wavelengths and multiple other parameters, which you would also not be able to immediately see on a wafer. So there's a couple of technologies we have developed with partners and also the correlations which then come into play when it comes to any subsequent processing steps. And then basically this wafer hits the chip making. And this is where all the fun starts, because once you start the chip making, you actually see whether this epi wafer is good, really good. And all the testing you have done before is meeting all the models and the experience you have built these models on. And then you see how many chips come out. Yeah, and that is
How
then
does it work? Do you interact directly with the companies that do the die bonding? How is the communication?
Yeah, so the interaction with our customers is actually very intense. Yeah, so we share in some cases even the raw data from the measurement equipment, because there is models which have been developed together to basically do all this analysis. Yeah, so whatever pixel would not light up later on, is it because of the processing, or maybe because there's something wrong in the epi, or some particle fell on the wafer on the way there, right? So there's really a lot of data involved, and it's funny that sometimes then people get actually to the limit of their storage system, and then they simply need to put it to the cloud. It's really interesting because some people we work with are also in the LED industry, and they are not used to this data crunching, which is completely normal in the semiconductor world.
Alexander, let's go to one of the market leaders in die bonding and understand how the communication from their side works. Travis Scott, from market leader on equipment for die bonding, fine tech, all the way from Berlin. Travis, thank you very much for being with us today. I am really happy to have you for the second week in a row on an online industry meeting. Tell us what you did in a particular market, but most important, how you could collaborate with Alos and with the rest of the people in the room. The floor is yours.
Hello, thank you, Jose and Olga, for the opportunity to speak here this week. Yeah, so I'm from FineTech. Just give me a nod if you can see the screen.
Yes.
Okay. Yeah, so I'm from FineTech. We offer sub-micron die bonding equipment with all of the process modules that go with that for various different types of bonding. Yeah, so for this week, we're focusing on the indium to indium interconnection, but we offer a wide range of high density, fine pitch interconnects. So this is everything from gold to gold, copper to copper, anything that you need to bring your micro LED displays to life. So we offer everything from the R&D process on manual benchtop systems all the way up to fully automated production. So we've called this at FineTech prototype to production. And we support the whole process with process development as well. Here you can see an example of a micro LED display that we built with a company in China. So these indium bumps are 2.5 micron diameter with a very dense pitch. I think it's about 7 microns. And then we have a technical partner that we announced last year at the Micro LED Summit, Light Technologies. They have a 1 micron indium pillar that they developed for their micro LED displays. So we offer a wide range of standardized process for this micro LED bonding, from cold compression bonding all the way up to reflow bonding with formic acid. The cold compression bonding was developed for the use of medical contact lenses and this kind of thing. And then, of course, for things like IR thermal imaging devices, we offer the formic acid to get the higher quantum efficiency and dark current to get the very high quality interconnect. And here we offer a standardized hardware and process solution, as well as paid partnership and process development for your technologies. So to repeat Jose's question, what can we do for you? If you have any interest in this kind of technology, please get in touch and we can set up a meeting where we can introduce this technology from you for our side, go through all the detailed questions and answers. And what can you do for us? If you have any kind of difficult or technical challenges that you face with your technology and you would like to test bed this with us on our die bonding system, feel free to get in touch with us and we can do some small sample runs or tests with you to see if we can solve some problems on your side as well. And also it gets us a better understanding of what's new and what's difficult on the market that needs to be solved. If you have any questions, I don't know if we have time.
We always have time for
Otherwise-
you, but
Okay.
Travis, thank you for bringing your die bonding here. We have questions for either Alexander and Travis, and I'm going to go first to a company that I'm really always very excited to have here at our meetings. Pospea is a company that provides design for fabrication of custom lasers in any market, but they are looking at the light engines on AR/VR as a potential opportunity. Betty, thank you very much for being with us today. Tell us your question and to whom the question is for. Betty, you're on mute. That's the sentence of the pandemic. We're back.
Hi, Jules. Thank you so much for the introduction. Yeah, I have a quick question for Valentine. I don't know if I say that name right. Valentine.
Yes.
Valentin,
Yes.
yes.
Yes. Thank you so much for your wonderful presentation. I have a quick question. Could you please help to comment on like what the integrated laser can do better in order to achieve your targeted parameters of your product in your last slides?
Is that a question to me?
Yes.
Yes.
Oh,
Yeah,
He's
so
talking
your
to specify
yes.
specify the light source that you are using for your
Yeah.
technology.
Yeah,
Well,
perfect.
yeah, we don't use lasers. I mean, in a general means. I mean, we use a micro displays. I mean, GBD micro displays. I mean, if we are talking about augmented reality applications. So then, of course, I mean, is that answer to your question? Or?
Yeah, so my question is like your last slides, you mentioned that your targeted like parameters is a
Yes.
smaller pixel pitch
Yes.
collimator. I'm wondering like what do you think an integrated laser can do? Because I don't know what kind of laser are you using right now, and I'm wondering like are you thinking about if there is any improvement of current laser that you can think of that can help you to achieve your next goal?
Yeah. Again, I mean, basically that's why I'm also here. I mean, it's like we do not really develop our own micro display right now. So we are basically looking for partners who can help us with that. I mean, our requirements are pretty tough just because, we need a display with the pixel basically less or at least around 1 micron and a pixel pitch around 1 micron or less. And that's kind of tricky and challenging. I mean, project, even though of course it's doable. So if we will be able at least to approach those modest requirements, I think that would really push our technology forward, and we can really enhance significantly the quality of the images delivered by our lens.
Indeed, thanks, Valentine. Betty, maybe after this meeting, we can introduce you to one of our corporate members that provides lasers for light engines in AR/VR, which is, of course, brilliance.
Yeah.
And thank you very much for being brilliant here, Betty, for being with
Thank
us.
you.
We have a question coming all the way from one of the best countries in the world. We are going to Poland. Arthur, coming all the way from Poland and the CEO of Q&A Technology. You have a question, a comment, and a potential room for collaboration. 3 in 1 with Allo Semiconductor. Arthur, tell us, voice your question yourself.
Yeah, thank you, Jose. We already interacted a bit with Alexander in chat, but my question was, what kind of wavelengths the ALOS technology can cover from the light emitting diodes point of view. So this was quite interesting for our technology, where we are looking at UV side of the spectrum. So that's why I was wondering if they can go down to 385 nanometers, for example.
What's your wavelength range, Alexander?
Yes, so basically our technology is gallium nitride. And with gallium nitride, you have a choice of actually tuning the wavelengths in quite a wide range. And the sweet spot is definitely in the blue range, right, where you have the highest internal quantum efficiency, 90+%. With green, it's a little bit less, but that is also for when you look in the LED industry, the material of choice for green LEDs is gallium nitride based. Yeah, you only increase the indium content in the multi-quantum wells, and there you go. With red, actually, there's more and more talk now with the micro LEDs of also using gallium nitride for red, which is something the whole industry would have laughed at several years ago. And with the industry, I mean the LED industry, because the efficiency is super poor, because the amount of indium you need to incorporate is just too high. And typically you go for the InGaN material system. versus the UV, you need to increase the aluminum composition, but that is still all gallium nitride-based crystal growth. And I mean, that goes all the way into deep UV with all the problems of lifetime and so on, because that is a really challenging terrain. But when you see what is happening there, even the deep UV, not even the 385 you mentioned, there's great progress. And 385 is absolutely normal range for nitride.
Alexander, what do you say? It is time to bring now our second integrator to the room. Let's do that. Let's go to the Sharp laboratories. We all remember the Sharp laboratories in the United States. Let's see what they had done with that. They had created a spin-off called ELOX Displays, and Paul Schule is telling us how they can actually make a revolution in saving power consumption. Paul, thank you very much for coming all the way from beautiful USA. The floor and attention of everyone is yours.
Thank you very much for that kind introduction and for remembering Sharp Labs, which does unfortunately no longer exists. ELOX has taken a path that is, in some sense, the opposite of Alos and Finetech. We are doing very large area displays, and we're trying to do them in some sense the simplest possible way. So let me share my screen here. Now, I have talked many times about fluidic assembly, and so I won't really be talking about that today. I'll be talking about cost reduction, and I think the points that were made earlier about defectivity are ultra important. And so what I'm saying is an alternative approach, and this takes us all the way back to what Ron was saying earlier about in micro LED, there are really a lot of approaches right now. So let me say two more things about what the approach we're doing here. First off, it's large area displays. What we do is not applicable to AR, VR, arguable whether you can even do it for laptop displays, say. Certainly, you would not want to do it for phones. The second thing that I will say is that the LEDs that I'm talking about today are not yet a display. So this is our step forward trying to make low cost. I'll start out by quoting from Eric. I think probably everyone has seen Eric Verre's presentations at different times. This is from the 2024 report on micro LED possibilities. And what he shows is a very rapid decrease in cost of micro LEDs, which I think is somewhat optimistic. Our 300 micron devices are actually somewhere between his 2026 and 2028 numbers. We're in here somewhere currently. But I'd like to talk about something beyond that. What I've called internally the Vire limit, which is the 228 square micron devices at these kinds of costs, $3,000. So back in the day of Sharp Labs, and I'm really happy to hear that name again. We talked a lot about cost because that was clear from the beginning. That was the limiting, or one of the very big limiting factors on micro LED displays. So we know, and the case we always made to Sharp Japan was that the lighting industry has done a ton of work on making LEDs. But of course, once you look in detail, there are a lot of defects and binning and wavelength range and so on that are problematic, and we'll get to that. So what we've done is we use a lot of inspection techniques, like Alexander talked about, to understand in pretty good detail what to expect of every LED on a wafer. And then with our harvesting process, we can prevent the bad LEDs from getting into the ink. We also have tried to go away from pick and place because the equipment is relatively large and relatively short throw compared to really big displays. That's why we went to fluidic assembly. And our latest tool is under $1,000. So that's kind of fun. But in order to get the costs down, you really have to use the MOCVD wafer more efficiently, and that means smaller devices. That's what Eric's slide says. So again, going back, what we came up with was what we thought was the smallest possible LED to do fluid assembly. And that's a vertical device, as Eric said. The device that we would see as the minimum we could do that was likely to have reasonable, not great, but reasonable EQE would be about a 20 micron area, vertical device. And you can see that it's a lock and key kind of an assembly technique that allows only the correct orientation of the device for it to be a live LED. The dimensions in the previous slide are a little too aggressive for the partners that we have. We don't have semiconductor grade steppers. And so, and also a 1 micron space for the gallium nitride etching is really unrealistic. So the devices we're working on now are somewhat relaxed. It's a size of 11 by 5 microns and 2 micron space. That seems to be workable. And right now we're maybe a little over 2 microns, more like 3. But this is the size of, gives us a cell area of 91 microns, which is pretty small compared to what people normally think about. Okay, why can't I scan? Oops. Okay. First off, there's the question of, can you actually align these things, or do you need to do pick and place? So this is where we are right now. This is a relatively recent result. We have these dummy devices that are the correct shape for our LEDs. This is a fluidic assembly result. At the bottom of the screen are empty wells that are too small to hold the devices. And as you go up by half micron bias steps, you can see that we can do the alignment. You can see things are pretty tight at 1 micron. And at the top of the page at 1.5 micron, you can begin to see spacing between the well and the LED. So I would argue that this is a reasonable kind of a tactic. Now, how do you deal with the defect? We do quite a lot of different things. Again, all the way through the process, you have a lot of data. You have photoluminescence at the begin from the MOCVD process. You have optical inspection for particles, for defects of different kinds. So we have a very large database. On the right-hand side are defects, on the left-hand side is photoluminescence, and we merge all of that together with the known alignment marks, the edge bead that's relatively conservative, and that removes LEDs from our population. And that's done with 2 different things. We use laser repair for single defects, and we print over the LEDs in order to prevent them from going into solution. I've talked about the selective harvest many times, so I won't talk about that here in any detail, of course. If you go through the steps that I just said verbally, you've got 4-inch wafer cost is around $200. That's maybe a little speculative yet because the final electrode processes are complicated, and as you might imagine, cost is still under discussion and negotiation. At any rate, if you subtract each of those loss mechanisms, our defect budget now is about 1.5%. The LED performance budget, we're throwing away around 10%. You can see the high and low emission areas in the PL that we're throwing away. But the bottom line is a 4-inch wafer at these sizes gives you 64 million blades. And so the materials cost is around $80. And our materials cost for a 30 micron disc, which is our other technology, is about 10 times that, little more than 10 times that. So down in the neighborhood of what the OLED guys believe begins to be economic for televisions. The harvest costs are low. It's wet bench. Assembly costs are low. The equipment is quite cheap and quite fast. So that is an alternate approach. Now, will we end up doing what I suggest? Probably not. But it's an alternative. And so when people say to you that micro LEDs are too expensive, you can say they don't have to be. Thank you for your attention.
Thank you, Paul. That's incredible. I like this resolution. Everyone tells you that it has to be expensive. No, it doesn't have to be. You've mentioned that you actually dissolve, or let's say that the LEDs are coming in the forms of the ink that you later print or somehow put on the surface. What would be, let's say, opportunities or the way to scale this really to the wall size displays for the outside advertisement?
Right. There's multiple things. The scaling would be some kind of a wet bench, like semiconductor wet benches. I currently do it one wafer at a time with tweezers, right? So it would be a wet bench with cassette, say 50 wafers, or more likely 25 wafers in a cassette. Certainly this process works for 6-inch wafers, works for 8-inch wafers. I'm not sure about silicon because we do laser liftoff, and so I'm not sure about silicon substrates. I think that can be done, but it's a little different. The thing about fluidic assembly is that it scales in one dimension, and so you need to make longer carriers, longer narrow carriers, so that the assembly direction is short. And so what you would do is you would scale your COC to be a longer piece, long and narrow.
Okay. Do you think it's eventually possible to use like inkjet printing for with these inks?
It is possible, probably, but I think it's more likely that this approach like we're using, where it's immersion, is probably the best. We've played around with inkjet. One of our people is an inkjet expert, and our solvent is very low viscosity, and LEDs, even in our sizes, are chunky. So it's quite problematic. You can do it. We've done it, but I don't think that's the solution. Something more like a pipette actually is what works very well, because you like a pipette for biology.
There is another question from Zahir. Zahir, please unmute yourself and ask your question. It's a good one.
Hi, I was wondering if you guys are only considering TFT, or are there other plans for maybe going to micro ICs in the future? And are you seeing that the TFT technology is actually good enough to make these displays, or there are some issues with it?
TFTs are, I spent many years working on TFTs, and so I would This is my personal belief, and it goes against what we're doing in our collaboration. My personal belief is that you want to use good quality silicon drivers because the TFT drive current just is not low enough for really high intensity displays. To your point, I believe that the LEDs are better than the transistors. So, but then you get into a cost question, right? Because we have to buy die from global foundries, which are significantly more expensive than Gen 10.5 glass. And so the cost trade-off question gets very complicated. And if you want to get that ultra bright display, then the cost is going to go up because of the drivers and the integration to get the current from the back of the display to the LEDs. In the end, the interconnection for using the silicon drivers gets to be tough. They're expensive. It's doable. People do it. We do it. But
yeah, that was the motto of your talk, how to decrease the costs and not how increase them.
Yes.
And since we're talking about inks and printing, and you've mentioned that, okay, that it might be an opportunity, but might be some limitations from the viscosity, I would actually like to introduce to the discussion and invite to the discussion a professional in inkjet printing, who is Patrick Gallagher, the CTO of Scrono AG, that they developed the new methods for the inkjet printing for the diverse type of the materials, also including for the displays. Patrick, please tell us more about the Scrono, and actually do you think its viscosity is a problem?
Yeah, thank you, Olga. I was kind of expecting that you would make that kind of transition. When I heard ink and inkjet printing, yeah, micro LEDs we have not yet printed, but yeah, possibly it can be done with our technology. Because it's not traditional inkjet what we are doing at Scrona, but we are doing so-called EHD. Some call it electrostatic. The proper term is electrohydrodynamic printing. So it's a printing technique that is fully electrical in its nature. So we're actually ejecting droplets by using electric fields and basically charge up the fluid to get it out. The process is basically a combination of what inkjet is already delivering today. So commercial inkjet printhead with a lot of nozzles that is scaling the throughput. It's the same concept like with other technologies as well. You need a lot of nozzles to be fast as you're depositing one droplet after the other. But it's in comparison to inkjet, it can indeed release certain aspects that are limited with inkjet, meaning viscosity, for example, particle size. Maybe that's also now talking about micro LEDs. I could imagine that particle size would be a problem for an inkjet printer that can be released with an EHD nozzle. And of course, it's about resolution as well. So precision resolution, that is what EHD can make much better than the traditional inkjet printing process. So how does it work? Compared to an inkjet printer, as said, we're using electrostatic forces. What we do with that is we overcome some of the more fundamental challenges of the inkjet process, the actuation of the fluid, which in an inkjet printer is done from the inside. So we're basically pushing fluid out. It's kind of, I always call this kind of the engineering approach. It's whatever engineer would do when you basically give him the task of creating small droplets. He pushes from the inside with a mechanical force. Now that creates a problem because you have a transducer basically. So you bring in, for example, with a piezo element, you bring in a mechanical force and you have to kind of translate it into a mechanical force into the fluid. And that again has to travel all the way to the nozzle until you actually create the droplet. So you lose a lot of energy on that way. And that limits the size of the nozzle you can use because at some point the resistance of the fluid to that kind of energy transfer becomes too large. And you actually also lose a lot of precision of droplet placement because you cannot give these droplets enough push anymore to hit them to the right position. Now with the electrostatic process, you get rid of that internal actuation, but you do something which I say is more the scientific approach, nature science approach. You're looking beyond mechanical forces. You try to create something mechanical that is actually not mechanical in its origin. So you use electrical properties of the fluid to create a mechanical response. That's really what we're doing. So we can create the energy directly in the fluid, directly at the nozzle exit. We can even focus it in a way that the traditional process doesn't, and create droplets that are substantially smaller than the nozzle itself. So that creates really a completely new system that gets rid of these fundamental issues of the inkjet printhead. We can create resolutions of less than a micron with the right inks, of course. And we can also process fluids that have more than, that are like honey from their viscosity or even more so. Now, what we are adding in particular at our company is the multi-nozzle perspective. So there are competitors that also use this EHD process, particularly, of course, in the microfabrication environment to replace, this kind of this reducing microfabrication process against an additive process. But it's way too slow if you have a single nozzle. So what we use again microfabrication, MEMS technology to bring these nozzles within a silicon package, you could say. And with that, we can, as said, replicate what makes inkjet printing so successful commercially. It's really a lot of nozzles working together. You can see here to the bottom right a video that illustrates the output of our 128 nozzle printer that we have recently released at the CES. So this is new. It's 128 nozzles that are operating fully individually. They're scanning the surface like an inkjet would do and deposit droplets according to a bitmap pattern that the printer receives from the software. That's it.
Thank you very much, Patrick. Patrick, what for these 128 nozzles, what is the surface that you're currently able to print at?
Well, the printer doesn't really care about the size of the surface you're printing on. The printer we use, where the printhead is embedded in, has a maximum movement range of 150 millimeters. But of course, the benefit of having an inkjet it's relatively our process particularly doesn't have strong requirements, for example, on the separation between the printhead and the substrate. So yeah, you also don't. It's very easy to integrate. So whatever your surface you would like to print on, as long as you have the right motion system, you can do it.
Thank you so much. And I actually would like to basically to wrap up this conversation, I would also like to bring into your partners that are providing inks that you're able to print. And of course, these are the Custom Dot that are developing our red and green inks. And Igor is here to tell to tell us more what are the recent advances in the inks that Patrick is then and Scrona are able later to print.
Thanks a lot for your intro. I'll be quite brief since I think we are running out of time here. What we do as Custom Dot is indeed we develop quantum dot based inks for color conversion applications in micro LED. Also, you can apply this technology to OLED to make quantum dot OLEDs. So what we do is we combine our expertise in quantum dot synthesis. We modify the surface of quantum dots and then formulate inks based on this. We believe today the most industrial relevant technology for mass production of display is inkjet. It's the most scalable technology. It is quite mature today. It has not been the case a couple of years ago, but today it is quite mature technique. And the first applications, first micro LED screens with color conversion will definitely be with inkjet printing. Of course, it has a lot of limitations. So we are working on other patterning techniques, other printing techniques to enable higher PPI applications. How far we will go, it's not clear today. There's quite a lot of routes. EHD printing is certainly one of them. It offers great resolution. and that's something that we are happy to explore with Krona, with others. It also has to be driven, of course, by the customer, by someone who is interested in applying this technique in their for their production process. So there, we really need that driver to do that. We also can help our customer in patterning process development, and then also we understand quite a little bit about quantum dot color converted devices, so we can help our customers get the best out of their devices actually. So we think together with the customer on solving their quantum dot integration problem, and then we provide inks for production of those displays.
Thank you, Igor. Igor, what do you think, let's say, are the roadblocks or the ways to, or the roadblocks on the way of perfectly marrying the inkjet or EHD printing with the quantum dots? Viscosity?
I mean, for inkjet, the biggest limitation is viscosity, certainly, because what we want to do is we want to make, so to realize the full promise of micro LED, we want to use a very small micro LED chips, right? So we want to use chips that are ideally smaller than 10 microns in lateral dimensions. It means that we cannot put a very thick quantum dot color conversion layer on top. So we want to have this layer as thin as possible, ideally a couple of microns only. Now, quantum dots, they're very good absorbers of light, but still cadmium-free quantum dots, you need to pack quite a lot of them into your ink to be able to absorb all the light. And then if we pack them a lot in the ink becomes super viscous. So making inkjet printable quantum dot ink for ultimate micro LED displays is very challenging. There's where techniques like EHD printing, which can allow higher viscosity, are very, very beneficial.
Okay. Igor, there's a question from you from Ron, but I cannot unfortunately call it out because we're running a little bit out of time, but please take a look at it. And I would like to call to the floor our last but not the least very important speaker, which is Artur Podhorodecki from the Q&A. And together with the custom dot, they make the red, blue, and green LEDs, and so the exact color code. Artur, so the floor of attention of everyone is yours, and for you it will be also then the question, okay, how do we perfectly marry Krona and the Q&A?
Okay, thank you, Olga. Hello, everyone. So Q&A Technology is a company who is developing blue light emitting quantum dots. We develop material, we do surface engineering, and also do inks. And today we meet to discuss about the micro LEDs. So if you look on the micro LED industry, there are two common approaches how to make image. So one is to use just a free RGB LEDs as light sources. And the other approach is to use just a blue backlight, and then you have to use red and green quantum dots. And both these approaches have some pros and cons. But there's another approach when you use the UV backlight to get RGB color. But in this case, in addition to red and green quantum dots, you need additional blue quantum dots to get a full color. And in my personal opinion, this approach is quite interesting because it brings a few advantages comparing to the previous two approaches. Using this technology, you solve a little bit the problem of spectral uniformity of chip, because the emission of quantum dots is pretty well defined and the absorption band is pretty broad. So it's not so sensitive to spectral properties of each LED on the device. Then you don't have the problem, which is quite serious problems to solve for the blue backlight, because you don't have blue light leakage in this case. In addition, the power consumption is lower than in case of native RGB approach. And of course, you don't need to put an additional structure, the filters on the top, just to avoid the blue light leakage. So you reduce the cost and complexity of the process. So there's a lot of advantages in this approach, but of course a few challenges. And one of them is to have high quality blue light emitting quantum dots. And this is what we do in Q&A. We are offering the blue light emitting quantum dots heavy metal free. We are developing these materials both for light conversion, which could be used for micro LED technology, but also for electroluminescence display, which is another fascinating technology, but maybe not story for today. In addition, our materials can be tunable, so you can really precisely define the blue color you need for your display. You can get a very high color quality using our material. We are already able to deliver material in a kilogram scale, but also open for R&D project for gram scale. And very interesting is also that we can deliver material in different solvents, but also monomers. So we can adapt to your technology. And this abilities to work with the surface of our quantum dots allows us to make inks. And one of our recent products are UV curable inks with already quite high efficiency, stability, and the common viscosity for these materials can be tunable between 9 and 20 cp, but we also can go lower and higher depending on what kind of deposition method are you using. And so far our inks has been tested by imprinting, inkjet, EHD, also working with Scrona, but also with the lithography lift-off process. So we proved that these materials are working pretty well with these methods. But if you're going to use this technology for AR glasses, you need to have a very small resolution. And there are some limits for printing, especially for inkjet printing. So that's why we are working right now on blue quantum dots based resist, just to use the common photolithographic processes, just to be able to get a very small pixels, which will be blue light emitting pixels. So this is what we're doing in short. If any of these materials are interesting for you, we'll be happy to chat and to be connected. Thank you.
Thank you very much, all the way from beautiful Wrocław in Poland. Patrick from Scrona, would you be able to comment on these two inks that were presented? What would be the challenges? What would be the Santa Claus Christmas list that you would give to them in order to satisfy your demands?
I think both things are quite well printable with the EHD process, also at very high resolution. It depends a bit. I mean, if you just have the quantum dots, you have extremely small particles. Generally, the way they are dispersed is creates for very stable inks that, of course, are also for our technology a necessity. So it's actually good materials. If you, of course, then you need to look at what else do you need to add into the, into the ink, scatters and so, which may tend to agglomerate or so. Those you need to take care of. But otherwise, I think kind of an acrylic matrix with a good, also a very dense filling. I would of course recommend that to get better efficiency in the layer thickness. Have a high filling in the ink, so which would not be possible anymore for inkjet then, as we have heard. Yeah, and then if you want to add other particles and stuff, that would then be something that you rather need to look at.
The last 20 minutes of this meeting with ELAX displays from the Sharp laboratories and then Scrona and then the two inks for me were the highlight of this event. Thank you very much, everyone. Two things. The first one, I'm going to run now to Mobile World Congress and stay tuned to my LinkedIn channel because I found out really, really fantastic things. The second one, you want to get in touch with any of the participants today, all you have to do is send us an email and we'll make the introduction. The third one, after I say goodbye to the YouTubers, some of you, you want, you can stay here in the Zoom room and we can have our famous private VR session. But allow me now to say goodbye to the people in the YouTube. Okay, my great IT department, please.